Hello and welcome to another session of ENGR Fluid Mechanics Recitation on Chapter 7. So in this chapter we learned about dimensional analysis and we also identified some of the key aspects of this process. The first process was the Buckingham pi theorem, which will help us identify the non-dimensional groups in the problem applicable to the type of problem we are using. And also towards the end of the chapter, we identified some of the key important non-dimensional numbers, for example, Reynolds number and Froude number or Weber number, depending on the situation we have. We're going to see those numbers in the analysis. So let's look at a problem where we try to apply the Buckingham theorem, at least for the first few problems. A thin elastic wire is placed between rigid supports. A fluid flows past the wire and it is desired to study the static deflection delta at the center of the wire due to the fluid drag. Assume that delta is a function of L, which is wire length, D, the wire diameter, rho, the fluid density, and mu, the fluid viscosity, and V is the fluid velocity, and finally E is the modulus of elasticity of the wire material. So you're asked to develop a suitable set of pi terms for this problem. So if you remember, there are certain steps we need to follow in order to apply the Buckingham pi theorem. So step 1 basically says we list all the parameters in the problem and we count them. Okay, so for example, you always have to remember you need to count the dependent variable as well. So if I write all the variables in the problem, I have delta, L, D, rho, mu, V, and E. So 1, 2, 3, 4, 5, 6, 7. So the number of variables or parameters in the problem are 7. So then step 2 says we then go ahead and identify these variables in terms of their primary dimensions. So for example, you can follow the MLT system, which I would prefer. If you're comfortable using the FLT system, which is force length time system, you could go ahead and use it, but I would rather suggest you do the basic thing, which is the MLT system, mass length time system. So if delta is the deflection, so it should have a length scale. So delta would be length, and L, we know it's a length scale, and D is again a length scale. Okay, and density we know is in the SI system kg per meter cube, so it would be m over L cube. Similarly, mu. Okay, so if you're not sure about certain units, you can go back to your book and see what units they have, and then you can always write it in the primary dimensions. And so if you go ahead and do that, the viscosity would be m over Lt. Okay, and similarly you can write velocity, which is L over T. Okay, and finally we have to write for E, the elastic modulus. So it has units of force per length square, so you can write in the basic MLT system as m over L T square. Okay, and elastic modulus comes from the fact that stress is proportional to strain, so the constant which shows up there is basically E in that proportionality, and then strain doesn't have units. Stress is force per area, it's like a pressure, so that's why you have elastic modulus with the units force per area. Okay, so if you look at the step, you have written everything in terms of the basic dimensions, okay, and then you see how many primary dimensions appear in the problem. So I see an M, right? I see an M, see an L, I see a T. So all the three basic primary dimensions appear in the problem. So that means my reference dimensions R is equals 3. Okay. So basically, by the Buckingham theorem, pi theorem, the required number of pi terms, okay, so pi terms would be basically k minus r, which is 7 minus 3, which is equal to 4. So you expect 4 pi terms in the problem. Okay. So next step is you have to select certain number of repeating variables equal to your number of primary dimensions. In this case, it should be equal to 3. And always remember, never pick the dependent variable. In this case, delta, which is what we want to find in terms of all the other variables. And also make sure the chosen repeating variable should not form a dimensional product with others. And also we should make sure we don't pick a dimensionless parameter. Okay? And also we should try to pick parameters that contain dimensions not including others, which kind of makes sense. For example, I can't pick L and D and rho together as one set of repeating variables, since L and D have the same dimensions, so you have a non-dimensional number there, L over D, so you should not do that. So you can pick any other combination which doesn't result in a non-dimensional group by itself. Okay, so that's the key thing here. So in this case, what I'm going to do is I'm going to pick L, rho, and mu as my repeating variables. And using this, I'm going to construct the pi terms, in this case 4 pi terms. And again, if you read the chapter in the book, there is no uniqueness to the final solution of the Buckingham theorem. All it says is the number of pi terms should be 4, but somebody might say they're going to pick D, rho, mu as a combination. That should work because those don't form a dimensionless group by themselves. So another way to look at is I can pick D, V, and E as my repeating variables. Even they don't form a dimensionless group. So you can see that you can come up with several answers, but as long as you can come up with 4 pi groups, you should be fine. And with experience, you'll realize which one of them is something which you can control experimentally, and you'll pick those pi groups. For now, let's go ahead and pick L, rho, and mu as our repeating variables. So at this stage, step 5 says you go ahead and find the required number of pi terms. So basically, let's try to find the first pi group. So pi subscript 1. Okay, so I'm gonna use delta, which is my non-repeating variable, and I'm gonna use my repeating variables L, rho, and mu. And at this point, I need to assign some powers to the repeating variables. Let's say A, B, and C for L, rho, and mu. And this is what we're going to do for the rest of the problem. Whereas the parameter here will keep changing until we get the 4 pi groups which we need in the problem. Okay. So the next step is, you know that pi 1 is a dimensionless group you're trying to find. So in MLT system, M, L, and T will have powers raised to 0, and then you go ahead and write what you earlier found for delta, L, rho, and mu in terms of the primary dimensions, what we did here. Okay, and then from there it's basically solving set of algebraic equations. Most likely they are simple in most of these problems. At most you have to do solve 3 equations and 3 unknowns. Okay, so I can write m power 0, L power 0, T power 0 for my pi 1, and L for delta, L power A for my L, and for my rho it would be n power B, L power 3B, and for my viscosity it would be m power C over L power C, T power C. Okay, and for both the sides of the equation to be true, in this case the powers of m should be the same. Okay, so they should equal to 0, L should equal to 0, T should equal to 0. Then you write these this equation here. So that would mean, by inspection, if you look at it, if you look for L, you have 1 plus A minus 3B, right, minus C. Since it's in the denominator, if you take it up, the power would change. It should be equal to 0, whatever is the power here. Similarly, I can find for the other two dimensions for M and T. Okay, and then at this point you go ahead and solve these 3 unknowns in the problem. You have 3 equations, so you can quickly do that. In this case, C is 0, that means B is 0, and then if you substitute these guys in this equation, you'll get the answer for A. Okay, and in this case pi 1 would be delta over L. Okay, and then you repeat the same process to find the next pi group. So pi 2 would be, now you pick another non-repeating variable D, and then you have L raised to the power A, density raised to the power B, mu raised to the power C. Okay, and you do the same procedure as we have done here. Okay, so again you'll end up with 3 equations and 3 unknowns, and if you solve them the way I showed it here, you should get pi 2 to be D over L. It makes sense if you look at these combinations, because the only way D and L and something else would be non-dimensional is when they're divided by one over the other. So this is pretty straightforward. Okay, but I would still suggest you write these equations so that you get the practice. Okay, so we found 2 pi groups. We still need to find 2 more. So pi 3 would be, now V is our non-repeating variable, L power A, rho power B, mu power C. Okay, so if you substitute the primary dimensions and then equate the powers to 0, you get pi 3 as V L rho over mu. so which is your Reynolds number. Okay. Okay, and then finally you find the last pi term. In this case, E will be your non-repeating variable and your other three repeating variables. Okay. So if you go ahead and do the solution again for this, and I would strongly encourage you try it instead of accepting whatever I write as the final answer. I would appreciate you practicing it. Okay, because I arrived at this answer by solving it just to save some time. I'm gonna go ahead and write the answer. Okay, so this would be E L square rho over mu square. Okay, and in all these terms, okay, I made sure at every step that whatever dimensionless group I got is in fact dimensionless, and you can quickly do that by substituting the appropriate dimensions and see if it forms a dimensionless group. Okay, so at this point we found out all the 4 pi groups which were part of the problem, right? So you have to finally write your answer in the form as shown. So pi 1 will be function of pi 2, pi 3, pi 4 in this case, right? So that means your pi 1 was delta over L will be function of B over L, VL rho over mu, which is your Reynolds number, okay, E L square rho over mu square, okay. So as I said, remember, if you picked another set of repeating variables which do not form a dimensionless group between themselves, your answer would be different. There is no uniqueness. But the key thing to remember is you should end up with 1, 2, 3, 4 pi groups in this problem for this specific situation. Okay, so that is a key step. So I would encourage you to maybe pick, after you look at the solution and you got a chance to solve it, pick maybe like D, V, and E as your repeating variables, and then see what groups of dimensionless quantities you get. Okay, all right, let's move on to the next problem. The water flow rate Q in an open rectangular channel can be measured by placing a plate across the channel as shown, okay, in this figure. This type of device is called a weir. The height of the water H above the weir crest is referred to as the head and can be used to determine the flow rate through the channel. Assume that Q is a function of the head H, which is shown here, and the channel width B, and the acceleration of gravity G. You're asked to determine a suitable set of dimensionless variables for this problem. Okay. So again, we'll go ahead and follow the steps which we did in the earlier problem. So step 1 is listing the variables in the problem, including the dependent variable, in this case the flow rate of water. So Q, H, B, and G. Okay. So you have 4 variables or parameters in this problem. Okay. So step 2 is you write each of these variables in terms of the primary dimensions. So Q is L cube over T, H is L, B is again L, and G is L over T squared. Okay. it is very key that you understand all these primary variables in the problem and make sure you know the units so that you can arrive at these dimensions in the MLT system. So you can see that at this point we have L and T as the only primary dimensions. We don't have anything in mass. So that means R is 2. Okay. All right. So step 3. So the number of pi groups we expect would be K minus R. So 4 minus 2. So 2. So we need to come up with 2 pi groups for this problem. So step 4, we need to pick 2 repeating variables, same as the number of primary dimensions in the problem, which was 2, L and T, right? So again, you have a choice here of picking H and G as your 2 repeating variables, or B and G, since they do not form a dimensionless group between them. Obviously, you cannot pick Q because it is the dependent quantity. So just remember, you can't pick that. Okay. All right. So I'm gonna do with H and G as my repeating variables. Remember, if you pick B and G, you'll get a different set of pi groups, but you should get 2 of them. Okay. So make sure you try with B and G as your repeating variables. So step 5 is forming these pi groups. So pi 1 would be Q H raised to some power x, G raised to some power y. Okay. So you will end up with 2 equations and 2 unknowns in this case if you follow the first example. So pi 1 would be Q over H raised to the power 5 over 2 G raised to the power half. Okay, so that will be your pi 1. Similarly, you can do pi 2, which would be B as your non-repeating variable, H and G. Let's give them some powers, x and y. So if you go ahead and solve, you'll get, obviously from inspection you can say B has a length scale, H is a length scale, so you expect this would be B over H. Okay. So at this point you have determined all the pi groups in the problem. So you go ahead and write your answer. Pi 1 is a function of pi 2, or Q over H raised to the power 5 over 2 G raised to the power half will be some function of B over H. Okay. So this is the 2 examples basically of using the Buckingham theorem. Okay, so you see that it's a simple procedure to apply as long as you stick by the rules and then you remember them, and if you go ahead and solve it every time, even though there is no uniqueness to the solution, at least you would get these non-dimensional groups figured out. Okay, let's move on to another interesting problem. So if you look at the previous problem, we write, even in the first case, we wrote in terms of some function of something. We really don't know what this guy is. Okay, so let's look at an experiment here. So the pressure drop per unit length, delta PL, that means force per area per length, right, for the flow of blood through a horizontal small diameter tube is a function of volume rate of flow Q, the diameter D, and the blood viscosity mu. For a series of tests in which D is 2 mn, mu is quantity shown here, the following data were obtained where delta P listed was measured over the length L equals 300 mm. So remember, this is the actual pressure, whereas this notation is this pressure per length. Okay, so we have to remember that. Now you're asked to perform a dimensional analysis for this problem and make use of the data given to determine a general relationship between delta PL and Q, one that is valid for other values of D, L and mu. Okay? So first we need to come up with the relationship between delta PL, Q, D and mu. So first we have to do the Buckingham theorem, which we have been trying to do in the last two problems. Let's apply the same thing, right? So we want to come up with delta PL as a function of Q, D and mu. Okay, so step one, you list and count all the variables in the problem, and remember you also need to include the dependent variable, in this case delta PL. So K is 4. So once you figured that, make sure go to step 2, where we write each of those variables in terms of the primary dimensions, in this case MLT system. Okay, Q is the flow rate, L cube over T, D is L, and mu is M over LT. So you see that MLT appeared in the problem, so that means number of primary dimensions is 3. So step 3, the number of pi groups we expect would be 4 minus 3, which is 1. So in this case we expect only one pi group. Okay, so step 4, you go ahead and pick number of repeating variables equal to your number of primary dimensions, in this case 3. So I'm gonna pick Q, D, mu. Since we have 4 variables and if it is only one pi group, the only choice we have is Q, D and mu. Okay, so whatever we determine will be a unique solution, at least for this problem. Okay, alright, so now let's go ahead and find the pi group. Pi 1 will be delta PL Q raised to the power A, D raised to the power B, mu raised to the power C. Okay, so if you do the math here, you'll end up pi 1 to be delta PL D square over Q mu. Okay, sorry, D power 4. I think I said D square, it is D raised to the power 4. And whenever you end up with one pi group, whatever this quantity is, it's equal to some constant C. Okay, and you can look at an example as well in the text for creeping flow where the Reynolds number is less than 1 or it is really small. Okay, so in this case we have to determine what would be this constant in the problem. Okay, so in this case we can then go ahead and use our experimental data. We know various Q values which produce various delta P's, right? So that would mean we can apply that, and we know D is a constant, we know mu, okay, and delta PL, remember it's delta P over L, So for each Q and P combination, you have to find C. Okay. So I did that for each of those 5 different flow rates. I get 5 different C values. Okay. And I took an average of those and I got 40.6. I encourage you to do it for each and see if you compute the average, you end up with this. And then once you have that, your final answer which you're asked to provide is this relationship between delta PL, Q mu and D power 4. Okay. If the experimental data were not given, we couldn't have come up with this number, which is this constant. Okay, all we could have said is we need to do experiments and determine what would be the relationship between these guys. Okay, so this is an experimental constant for this problem. Okay, if you use some other, if you design some other experiment, you might end up with a different C, but for this problem, this is what we have. Okay, all right. Let's move on then. A model of a submarine 1:15 scale is to be tested at 180 feet per second in a wind tunnel with standard sea level air, while the prototype will be operated in sea water. You're asked to determine the speed of the prototype to ensure Reynolds number similarity. Okay, so again, you see this is a great application of what we have been learning in this chapter is you don't necessarily have to test on the prototype. You can build a model which is smaller than the prototype and you can simulate the flow physics for your actual prototype or flow fields you expect for the prototype. Okay, and that was the whole goal for us to learn concepts in this chapter. Okay, so if I denote subscript M for the model and P for prototype, right? You want to ensure Reynolds number similarity. That means REM for the model and Reynolds number for the prototype should be the same. And the definition of Reynolds number, it's a non-dimensional number, U L over mu m. You can use mu over rho as well, which will be the absolute viscosity or density. It's the same thing, you'll end up with the same answers, but I've used the kinematic viscosity, so will be equal to the Reynolds number for the prototype. Okay, and here we know that we can find the kinematic viscosity for the model because it's air, and we can find it for the prototype because it's going to be operated in sea water. Okay, and another thing we were given in the problem is Lm over Lp is 1 over 15. Okay, so this is the length scales we are given. So from this we can write the unknown, which is the speed of the prototype, from this Reynolds number similarity as the following. Okay, so at this point we know un, which is 180 feet per second. Maybe I should write it here. It always helps if you write whatever is given in the problem, so that you write 8 here. Okay, it helps you. And at this point you can go ahead and look up the tables. I think table 1.7 and 1.5 for these kinematic viscosities. Okay, and then substitute in this formula. So UP will be 180 times 1.26 into 10 to the minus 5 feet square per second, the kinematic viscosity of air, divided by 1.57 into 10 to the negative 4 times 1 over 15. Okay? So if you punch in the numbers, you should get UP as 0.963 feet per second. One quick comment I think is you can see that for a really small velocity which is expected in for the prototype, you have to go orders of magnitude in terms of velocity for your model. It's something to think about. Alright, so this is a problem where we were asked to do the Reynolds number similarity, that's why we did it. But then as we learn these concepts and as we go along and maybe find a career in fluid mechanics, then you would actually decide what are the important parameters in the problem, and then you want to explore based on some analysis. And also we will learn when we look at chapter 6 about some equations and which terms would be important, and you'll understand this much more better when we cover that as well. Okay. Now let's look at another problem. A thin layer of an incompressible fluid flows steadily over a horizontal smooth plate as shown. The fluid surface is open to the atmosphere and an obstruction having a square cross section is placed on the plate. A model with a length scale of 1 over 4 and a fluid density scale of 1 is to be designed to predict the depth of fluid y along the plate. You're asked to assume that inertial, gravitational, surface tension, and viscous effects are all important. What are the required viscosity and surface tension scales? Okay, so this statement here tells you that Reynolds number is important, Froude number is important, and Weber number is important, which includes the surface tension effects. Okay, so let's go ahead and write Reynolds number is important, Froude number is important, and Weber number is important. That means for this model and prototype to work together, you need to do the Reynolds number similarity, Froude number similarity, and Weber number similarity. Okay, and in this problem, you're asked to find mu m over mu p and the surface tension scales for the model and the prototype. Okay, so let's go ahead and write the general definition for the Reynolds number. Will be rho v L over mu, right? For Froude number will be v over square root of g L, and Weber number would be rho v square L over sigma, okay, the surface tension. So for us to solve this problem, we need to make sure REM is equal to REP. Similarly, FRM is equal to FRP. That means the Froude number for the model and the prototype should also be matched. And similarly, the Weber number for the model and the prototype should also be matched. Okay. And what we are given in this problem is Lm over Lp is 1 over 4 and rho m is equal to rho p. Okay. So I can go ahead and use this, or if you look at the text, you look at examples where you can find some other way to do it. But if you look at this problem here, you first have to somehow come up with what would be the velocity scale. Okay, and then you'll see that you can then use the Reynolds number and you can come up with the viscosity scales. And once you know that, you can use the same thing to come up with the surface tension scales. Okay, when we solve it, it will make more sense. Okay, so if I equate the Proud number similarity here, I get Vm square root of G. Let's assume we are doing everything on Earth. G Lt. So these square root of G's cancel. So you'll come up with a relation like this. Okay, and you already know about the ratio of Lm or Lp. If you do the math, you'll get the ratio of the velocities between the model and the prototype is as half. Okay, you can use this fact, okay, and then use the Reynolds number similarity, right? And then you'll end up with mu m over mu p as 0.125. Okay. Okay. Let me solve the other part of the problem as well. And we have to find the surface tension scales. So WEM is equal to WEP. If you do that, you can then find sigma m over sigma p, the surface tension scale for model and prototype, as I won't write the decimals here since I'm running out of space, so it would be 1 over 16. Okay, or if you want to have in terms of decimals, it would be 0.0625. Okay, so this is how you can solve this particular problem. Okay, let's look at another problem. And I realize that this figure here is not the one which I wanted to show up here. This should have been with the previous problem. So let me see if I can, let's not worry about it, but this doesn't apply for this problem. This should be for the, I think, 762. Okay. Yeah, it should be for this one. Okay, so let's not worry about that. Let's look at this problem. A 1:40 scale model of a ship is to be tested in a towing tank, and you can look at the video if you're interested. Determine the required kinematic viscosity of the model fluid so that the Reynolds number and the Froude number are the same for the model and prototype. So we have done a similar thing in the previous examples, but we have one less parameter or non-dimensional number in this case. You're asked to assume the prototype fluid to be seawater at 60 F, and you're asked to investigate if any of the liquids with viscosities given in your figure B2 in appendix can be used as the model fluid. Okay. Again, for people who might not look at this video, this is the figure for 762. Okay. All right. So what are we given in this problem? We are given the length scales. So Lm over Lp equals 1 over 40, and you're asked to find mu m. what we are asked to find based on Reynolds number, similarity, and in this case, as you remember, Dr. Senechek told us in class, or told you guys in class, that when you have length scales like this, you generally represent it RE subscript L. In this case, we know that, but instead of avoiding confusion, because we have to deal with model and prototype, are not using that convention in this case. Okay. Again, we have to have the fruit number similarity as well between model and the prototype, so I'm gonna include that. Okay. So you know the prototype fluid, seawater, so you can find mu P from the tables, okay, in the front of your book. So this is what you'll get. And the Reynolds number is VL over mu, and fruit number is V over square root of GL. Okay. And if you look at an example in the book, they automatically give you the similarity relation, what you expect in terms of the ratios of kinematic viscosity, but let's go ahead and do it. FRM is FRP, right? From there, you can determine Bm over Bp as square root of 1 over 40, and then you can use the Reynolds number similarity for the model and the prototype, okay, and you'll come up with this for the kinematic viscosity for the model as Vm over Vp, Lm over Lp, nu P, we know this guy, we know this, we just found out this as square root of 1 over 40. If you put in all the numbers, mu m, or the kinematic viscosity of the model, comes out to be 4.62 to 10 to the minus 9 meters square per second. Okay, and if you look at the figure in your appendix B, you'll see that this value is much lower than most of the fluids there. So we can say no fluid is applicable from what we have in the book. And I would encourage you to go back and look it up and confirm this, right? Okay, so those are all the concepts which you should know, and these are some of the problems which you probably should try to accomplish in this chapter, and it will help you as well in the coming exam. All right, good luck for your test. See you in class. Bye.